So yeah, in case you were wondering, this is not the NLP talk. This is Windows CE. I have to apologize for making them switch at the last minute, but I happened to sort of look at my schedule yesterday evening and I suddenly saw this breakfast I was kept plugged in for, and then I thought maybe there's a talk following that, and that was the first I actually realized that I was talking today. So the rest of my day was somewhat double, triple booked already, and so I have to sort of move things around a little. Of course, it also means that the slides were generated at 1 o'clock last night, but hopefully they'll be fine. I didn't have a really good idea of what you people really wanted to know about or talk about. So what I've done here is I've put together a little bit of a framework for giving you a good sort of perspective of what Windows CE is, what kind of features it has, how low it goes, how high it goes, what we're thinking of doing going forward, and sort of a little bit of a history Dan wanted me to give of how we got here. I'll try and keep the presentation itself a little shorter so that we can have 15-20 minutes or something to delve into any other topics that you people really want to get into. And I guess I talked with a few people this morning to get a little more of a feel for what you wanted to hear, and so I'll try and concentrate a little bit on, it seems like the low end of the OS is what you're a little more concerned with or interested in. So the agenda was sort of easy to come by from the topic. So we'll talk a little bit about the past, just a brief trip through the products we've already shipped and where we are right now in terms of the evolution of the OS and the entire strategy really regarding Windows CE at Microsoft. The meat of the talk really is sort of an overview of our current strategy and architecture for the operating system, the one that we're shipping right now. And then I'll spend a little bit of time on what we see as our big challenges and big issues for the OS over the next couple of years, and what we're thinking of doing to address most of these issues. So the first Windows CE related product to appear on the market was in the September of '96, and that was the handheld PC version 1. I don't know how many of you have ever seen that. And that was the culmination of probably 2 years or so and lots of different efforts which sort of died and then had rebirth in the form of Windows CE. But this was a very integrated product. It didn't have a huge amount of separation, so to say, between the OS and the apps. It was one team, and we made trade-offs in the OS. We just tested it in the context of doing a handheld PC. In terms of the size, the OS part of that code was probably about 1 megabyte. It ran in about a working set space of 400K or so. This is sort of including the shell and everything under the Win32 API layer that you might think of. But this was a very seminal product for us because this was the product for which caused us to develop most of the code base, which is part of the OS now. We've done lots of rearrangement and tweaking since then, but most of the major modules were developed and enforced for this release, including the kernel, the window manager, the communication stacks, and most of those kinds of things. After that, about 6 months from then, in March of '97, we started. We had the first product reflecting a little bit of a divergence of the OS and apps. So this was the first instance of us taking the OS and creating a separate team, and we actually physically created separate teams in the organization. We started trying to do what we call a componentization of the OS, try to make it a little more adaptable for different kinds of targeted devices. Because it was about this time that we realized that we were going to have more than one device. This wasn't just going to be a handheld PC operating system. It was going to try and scale across a lot of different products at the low end of the device space. And the first product, the only product really which shipped on that OS was a J version of the handheld PC, which we shipped in March of '97 in Japan. Then a major milestone for the OS as a standalone product was our 2.0 release, which we launched really at Embedded Systems in October of 1997. This was the first time that we completed sort of the OS and app separation, and we shipped the OS as a standalone embedded operating system product, shrink wrapped to the world. And we had to go through and set up a whole lot of infrastructure to allow OEMs to work with us, support infrastructure, system integrators on all of those sorts of issues. Internally also, in this time frame, we had a lot more divergence of products coming out from Microsoft based on Windows CE. On this operating system, we shipped the handheld PC version 2.0, which some of you might be familiar with. We shipped the palm-sized PC 1.0, which just shipped recently and is probably hitting the stores anytime now. And we also shipped a J version of a Japanese version of the handheld PC. And in fact, the Auto PC, which hasn't yet shipped, is also based on this version of the OS. So this was a really crucial milestone for us. Our componentization strategy was a lot more mature at this point because we were addressing a lot more products. And we had, I'd say our feature set probably reached much more of critical mass in this release. We sort of rewrote GDI, rewrote lots of things to make sure we could address the width and the scale of the different products that we wanted to have.
Sharad, how big is the OS now? Megabytes?
In 2.0, the full-featured OS is probably about 1.5 megabytes.
Working set about the same still?
Working set is actually about the same, maybe even a little smaller, because we do a little more paging now. In 1.0, we didn't do that much paging.
So what would a minimal configured OS?
I have lots of slides on this.
What do you page to?
No, we page in, not page out.
Okay.
We don't just...
Do you have any pictures of the actual devices?
No, not really. I sort of targeted this talk more at the OS level.
Right. That
rather
would
than
be
the
helpful
product
for
level.
context. I don't even know how big the device is that will be.
Okay, I can give you a little bit of context on
How
that.
much memory they have.
So the handheld PC 1.0 device was 4 megabytes of ROM and 2 megabytes of RAM. Out of the 2 megabytes of RAM, about 1 megabyte was used to simulate an object store or file system where you store your data, and about 1 megabyte was used as running RAM memory for the applications. The handheld PC version 2 doubled from that, so it has about 8 megabytes of ROM and 4 megabytes of RAM. Again, split sort of half and half, although you can change the configuration of how you split your memory usage between object store and actual application memory. The palm-sized PC is pretty much about 4 megabytes of ROM, and they vary from device to device, but the smallest ones are 1 megabyte of RAM. So they have about 512 kilobytes of application space and 512 kilobytes of object store. Now, various other devices have completely different characteristics. Like we have a game player which we just announced with Sega, the Dreamcast, and that has 128 meg of RAM, synchronous DRAM. In fact, it runs at CPU speed. Most of that is used for the texture maps and the rendering and all that kind of stuff. The OS, in fact, is stored in a serial PROM from which we page it out to real memory. So the characteristics of the devices vary a lot across the entire chain. In terms of processors, to give you a different perspective on the same thing, the handheld PC version 1 shipped on the equivalent of like a MIPS, 3000, MIPS 3100, MIPS, those kinds of devices, running at about 32 megahertz. Some of them with 16-bit data buses. The handheld PC version 2, most of them have gone up to probably about 60 megahertz or so. Things like the game player run on an SH4 200 megahertz power. So there's a wide sort of scale even as far as. But going forward, things like cell phones want to run on ARM processors running at 19 megahertz. Or, so there's a fairly wide variety. Yeah.
That's kind of been the crux of some of our questions, I think, which is That's the sort of how far down it goes. That is this the cell phone OS or the light switch?
Right. So
OS?
I think let's get through this, and then we'll talk about it. So the present is really Windows CE version 2.1, which really is actually shipping any minute. This is part of why I've been quite busy lately. But the final bits are actually in the lab, and we think we're going to ship Monday morning. So that's fairly exciting for us. So I'm going to talk now, and I might breeze through a bunch of these. I don't necessarily think I'm going to go into all the different features and throw all kinds of this API support and stuff like that. But I want to just give you a little bit of an idea of the depth and the kinds of features that we support in the operating system. Our strategy in general is twofold. One, from Microsoft, in terms of our CE strategy. One is to develop a general purpose embedded operating system, Windows CE, sell it as an independent product, and make it address the needs of the embedded market, try and make it go as low as possible, try and get to the sort of non-Windows device category out in the open market. And that includes not only the OS, but the tools to sort of allow you to develop for it and everything of that kind. To make this happen, we're developing several key partnerships, lots of hardware, software manufacturers, chip vendors, system integrators, and lots of other different companies and OEMs, of course, to try and extend the reach of the Windows CE OS. At the same time, however, we have a fairly wide and concerted effort at Microsoft to have focused, targeted products which use this OS and highlight the use of the OS in different device categories. And we've already talked about several of these, like the handheld PC, the palm-sized PC, the auto PC, the game player. We have a DVD player. We have the web TV, set-top box. We have a web phone, which is more of a home product with a web browser in it. So we have a really wide variety of products which we're sort of OEMing from Microsoft, where Microsoft is the virtual OEM. We actually decide what the device would look like. We decide what the look and feel of the device should be. We decide what the API set supported in the device should be. We evangelize them as platforms, go out and get ISVs, go out and sign up OEMs to actually build the hardware, and then physically sort of are responsible for the delivery, the marketing, and the channel, all of that kind of stuff. Yeah.
So I'm trying to figure out what the term Windows here signifies. Are you trying to suggest that there is significant compatibility with normal Windows at the API level?
Next slide.
Okay. And also code base. What sort of
I'll talk about that. When I cover each module, I'll sort of give you maybe a little bit of history on where the code base came from for that. And so there's sort of this twofold strategy. In terms of the number of people we have, we probably, in Harel's division, we're probably close to 300, 400 people. And by the end of this fiscal year, we'll probably be closer to 500, 600 people. Of those, about 70 or so are in the OS product unit itself. The other 400 or so are in targeted product units. So most of the people, there's a lot of people working on these different targeted products. One of the reasons we have so many targeted products is, of course, we want to be in the game of being in the high-volume specific device categories that we think make sense, but also because we use our internal products to sort of flesh out the OS and get the OS into shape and tell us what we really need.
When you say 70 people in the core OS group, the common pieces of code, do you consider the people who are doing the Pocket applications and stuff part of that group?
No.
So that's also
when I say OS, I'm talking mainly about everything under sort of the Win32 layer.
Okay.
Not even including really a whole bunch of shells and stuff, but that also we'll cover a little bit more in detail. And all of those 70 people in the OS group, probably about 20 or so are developers. So the core OS development team is not that big, but. And I'll go into this one a little bit later, more in detail a little later. But till now, the embedded systems market has really been mostly about how small you are in terms of RAM, ROM, and what your latencies are. It's been a very, very sort of low-end market. And while we try and compete on those fronts, we are also, in some sense, taking advantage of and trying to change the landscape of that market a little bit. Independent of us, the embedded market also has started getting much more feature rich. You know, if you go and look at the operating system offerings from ISI with PSOS or Wind River with the Xworks or QNX or anything, you'll find that whereas all of them started off with really small 20K kernels and they can still do that, most of them are spending a lot of their energies on doing windowing APIs and high-level protocol stacks and connectivity to the internet and a lot of these sort of high-level features in the OS because a lot of embedded devices and products in the sort of space we're talking about want those kinds of things. So also we try and go after the fact that we are somewhat hardware agnostic. So we try and support more CPUs, give people more choice between evaluating different hardware possibilities like the processor and being more competitive in that sense. And then of course we try and leverage our hardware-software integration, sort of our developer evangelizing machinery from Microsoft and all that kind of stuff. But we'll get into this a little more in detail. So down to the architecture. The first sort of guiding principle we have is we try and be as compatible at the developer level with the Windows Win32 API. So that's where the term Windows comes from. We evangelize ourselves as being very much a member of the Windows family, sort of Windows NT, Windows 98, and Windows CE. And at the developer level, we get a huge amount of leverage from the fact that we aren't inventing new paradigms in terms of the programming API. So that's probably the single biggest advantage Windows CE has over anything else. The fact that there's gazillions of developers out there who know this API, who know the paradigms, who know the tool set, and so we try and leverage every last inch we can of that. So if there's anything has been done in the Windows desktop OS, we will typically try and do it the same way. Now that doesn't mean that we're going to take exactly the same code and put it there, but it means that as far as the user is concerned, we'll try to keep the semantics as close as possible.
What is your tool set today? Are all of our tools supported?
Pretty much, yeah. VC is the development environment. There's obviously plugins because VC only supports x86, so we have to plug in lots of different backends for the different chipsets that we support.
VB, VJ?
Yeah, pretty much. The second big feature or architectural principle for us, and I should have got a glass of water. Can someone actually fetch me? I'm going to go first in a couple of minutes otherwise. Is to make the OS as scalable as possible. So, and I'll go into a little more detail on this, but to allow this OS to address the needs of all the devices we have, not only, even just the devices we have internally, and all the target OEMs that we're trying to address outside, we have to do a lot of things to try and allow the OS to scale nicely across a wide range. And we'll talk about, how wide a range we're trying to scale and, where the upper and lower limits for that will come. The third one is the communications part. And this is, obviously the internet revolution has sort of affected all these things. Our OEMs, HP wants to have all of their logic analyzers stocked in the internet because that's where they want to download, updates from. They want to, everything wants to be connected to the internet, and everything wants to be connected to everything else. And so there's a huge amount of push to have, even in the lowest end devices, some amount of basic communication capability. And so
that's a great question. What is the OS that's running in these instruments now? Like they were using Sheraton's V system for a while. And
you'll actually be surprised, but a lot of HP's logic analyzers run Windows NT.
Okay.
Was that ROM version they did where they took out the page file and whatnot? Or?
Some of them actually almost run the full NT. But those are the high-end logic analyzers. The lower-end ones have several different OSs. And that's another one of our sort of draws. We're trying to say that for companies like HP, which have a wide variety of devices, where we'd like to give them an opportunity to standardize on a single OS which can work well across the range of devices instead of having to have specific OSs for different classes of devices.
Can I?
Yeah.
You may want to defer this, but it seems to me that more and more of these devices are going to have to be less solipsistic than current PCs are. Yes, they link to the internet, but there isn't really a lot of machinery that thinks of these devices as aggregated and working together. If you think of game controllers or telephones or other kinds of embedded systems, almost even more than PCs, you think of support for this kind of aggregation and collaboration. So I'm wondering where that sort of capability starts coming in and where you have to think about distribution and distributed systems and not just really small, fast, componentized little OSs for
Sure.
devices.
I think I'll defer that, not only because I think some of it might be covered, but also because I don't have a real good answer right now. So,
Okay. But I think that at one level, it was actually, I think, tech maybe that I was thinking of that Sheraton sold his V system to, and they had a whole bunch of broadcast TV analysis equipment that was running, a distributed operating system. And one of the cool things was you could just put a big PC on the desk beside it and essentially plug it on the same bus and have it talk TCP/IP to the instrument. And so, at one level, it seems that network protocols.
Yeah, but is that
Do this.
sufficient?
I don't
You
know.
say you have an IP device.
Well,
Does that solve the problem? I
If
don't
you
think
have,
so.
if you have DCOM on top of that,
That's the kind of thing I'm asking.
Right,
Exactly.
And I think that's the trend he's riding on, because the issue is really bill of materials for these devices. And with the decrease in cost in RAM, ROM, and processing, the increase in costs are programming and communication, subsystems, and other things. So by being able to run on a standard platform, you can really ride the trend down rather than ride it up.
And I think we will cover some of these points, and I'll talk a little more about our communication stuff and COM and DCOM and things like that.
We're assuming the whole thing is built on DCOM, right?
Not right now.
We appreciate these.
And of course, to be able to address so many different hardware platforms, we have to be as easy as possible to port different hardware platforms, to be as hardware agnostic as possible. And you should never underestimate the importance of trying to be small and fast.
Sharad, how much of your code is ASM versus C?
Very little of our code is assembly. It would be a nightmare for us to support 6 different processor
Do you have
families.
a HAL-like layer as NT does? Is that how you do it?
Yeah, Nick, I'll cover that.
Okay, thanks.
I think we're going to be here for a couple of hours. But, we'll see. So the Windows API compatibility, said it's a familiar Win32 model. It's the same executable file format, the same process thread model. You might ask, how did we decide how to sort of support the API set that we support? The really simple answer is that we paged the API set in. So as we did devices, as we wrote applications for it, as they needed APIs, we first of all would always push back, then say, is there any other way to do this? Just keep the API set as orthogonal as possible, as simple as possible, and as small as possible. Now, in the actual Win32 API, there'll be 7 ways of doing the same thing. We try to have exactly one way and eliminate the other 6. We believe at this point we've sort of crossed the knee of the curve. We typically find that most people who try to port applications now don't have requests for extra features or extra APIs from the OS itself. And we have fairly sophisticated applications now running on this, things like all the Pocket applications and lots of ISV applications. In terms of how we develop it, that's the other compatibility point I was talking about. It's the same Windows IDE. We have plugins for BCV, VBJ, and allow people to develop for that. And that's a big plus, but it's also sort of a minus. When you get to the real hardcore embedded market, the tools for doing hardcore real-time programming are very different. And VC doesn't really work that well necessarily when you get down to that level. And so while it's a big plus for us to have this sort of bootstrapping, it's also a minus in that we don't have any expertise at Microsoft in the tools addressing that low segment. And right now our strategy for that really is to talk with the vendors, tools vendors who do embedded systems tools, and get them to port their tools over to Windows CE. So that we can have a much richer offering of tools there.
Do you find that one of your, or maybe it isn't a problem, I was just going to guess that one of your bigger problems is apps that have now gone to rely on being able to allocate huge chunks of memory and not worry about it and let the paging system take care of it?
Yes, we don't advertise ourselves as you being able to take a desktop application and just move it over. You have to do some amount of rewrite. If you write an application with keeping in mind that you wanted to run on Windows CE and the desktop, you could have the same code base, which you just compile twice. But yes, you do have to specifically deal with memory management at a different level on a Windows CE device than you do on the desktop.
What percentage is that number, 1,500 number?
It's probably about, the Windows API set, there isn't a very good definition of how vast it goes, but I'd say probably
Today it's...
Well, I think a more appropriate sort of answer would be for things like user and GDI, we probably have about 50% of the APIs. For things like kernel, we probably have about 75% of the API. We don't have huge sort of entire sets of APIs, like we won't have MAPI or we won't have things like that. But of the systems that we support, we typically would have about 50% or so of the APIs.
What version and how complete is the WinSock support?
It's WinSock 2.0.
Focusing on Pocket PCs and things, are the Microsoft apps groups writing the apps now, or are you still doing it?
Right now, a lot of those 400 people are writing these Pocket apps and the other things. And that's mainly because till now there wasn't enough momentum in Windows CE to get the Office group to really even give us the time of day.
Not enough market in some sense.
Not enough market, not enough money. When the Office group basically bills by the hour. So in the long term going forward, yes, we would like to be taking more advantage of the different parts of Microsoft. So we'd like to move a lot of our tools efforts and integrate them with the desktop tools and have them sort of take charge of doing the plugins for developing for Windows CE. We'd like the Office groups to sort of develop the Pocket versions of their applications. And we're sort of on the path there. People do give us the time of day now, especially at the VP level. They start at least looking and keeping them and keeping Windows CE in their sights as something to look at. And so, assuming we don't flop on our face, I think in a few years probably we will see more migration from Windows CE out. And of course, that's the only way for us to scale going forward. We can't always sort of keep on redoing things. So I want to talk a little bit more in detail about componentization, since this is one of our cornerstones, really, and something which has a huge impact on our scalability and how we address different market segments. And the need for this really grew out of, initially, just the fact that I have a single OS development team and I have 400 people in 7 different product teams knocking down my doors. All of them, of course, think that I exist only to supply them with an OS. And this is a hard situation because we want to have a single code base and we don't have the testing resources or the development resources to really develop 7 different custom OSs. And so we had to come up with some sort of a strategy to allow the same code base to scale across these different devices. What we have really is, when we build the OS, we don't build it as a bunch of exes and DLLs. We don't have a kernel.exe and a user.exe and a gdi.exe. We build the whole system as a collection of about 200 different components. And then we essentially give the product groups a Chinese menu where they choose what components or what functionality they want from the OS. Now, it sounds really simple on paper, but of course there's a huge amount of complexity in terms of doing all the dependency analysis between these modules, writing them so that they can be taken apart, and much more actually than the development complexity is the test complexity of testing a bunch of 200 components which can be put together in 2 to the 200 different ways if you really just gave people the flexibility of doing that. So, but sort of from a bits standpoint, that's what we do. We just ship a bunch of libraries, and then you select which ones you want. We do the dependency analysis and select the the superset of what really is required by you, and then we link them together appropriately to create modules. That's sort of at the bit level what happens. So when you get the OS, the ETK, our embedded toolkit, is the shipping vehicle for the operating system. When you get that, you just get this whole huge bunch of libraries, and then you write this configuration file, and you run what we call a sysgen process, which then creates the operating system or links together the operating system from the different components. Now, not only do we sort of just link together these components, but we carry this forward, or carry that same componentization concept throughout the OS. So we'll take all the header files which are being used by the OS, and we'll strip out everything that you haven't selected, which isn't exposed by the OS that you've configured. Not only that, then we'll take all the import libraries and we'll strip those out. We'll take, we have our toolkits and our VC and VB add-ins. They take a configuration file. So when you're developing for the OS that you are trying to ship, you tell VC what configuration you're running, and it won't allow you to use any APIs or things that aren't available in the OS.
So this means when you're developing, you have to have that particular OEM's header files before you can really write an app.
Well, you don't need his header files. You need his configuration
files.
Correct. So when you open VC for Windows CE and you want to develop an app, right now you'd have to tell it, I want to develop for the handheld PC, or I want to develop for the Sega machine, or I want to develop for something else. And if an OEM shipped you a configuration file and wanted to enable an ISV community for their platform, then they would ship that configuration file, and ISVs trying to write to their platform would use that. But what that means is that once you've actually gone through the sysgen process, you have a custom OS. For all intents and purposes, that OS only exports things that you want it to export, from the development standpoint, from ISV standpoints, from every standpoint. Other useful sort of effects of having componentization, it allows replacing of components. So we can ship a set of components, and then for some subset of them, we can really document it well enough that someone could, an OEM who wanted to replace or modify the behavior of a specific part of the OS, could then just replace that component. And a good example for this is sort of the low memory handling. So we have a component which does low memory handling in the system. And for different devices, what you want to do in low memory situations could be different. On the handheld PC, when you hit a low memory situation, it brings up this sort of system modal dialog saying you must kill something, one of your applications, because we're running out of memory. On the palm-sized PC, it's just because there's no concept of multiple running applications visible to the user with a taskbar. They replace that component with a different behavior where it just enumerates which are the applications which were least recently used, which aren't visible, and sort of kills them in the background automatically. Now, as an OEM, depending on your device, you could do different things. Similarly, you could take something like the exception handling message box. What happens when something like that happens? When an exception happens and you want to put up a message box, on some devices like the Auto PC, where it doesn't have a full screen, it just has a two-line LCD screen, they've replaced the message box component, so they can have their own version of what actually gets displayed whenever someone wants to put up a message box. Similarly, obviously at the controls level and the window manager level, products like web TV or anything running on the TV, you have to do controls in UI in a different fashion to allow you to look good on a TV screen. And so they replace, for instance, all the non-client painting area, the non-client component, so that the windows have a different look and feel when they run on there, but the base window manager code is exactly the same. And finally, of course, having all this componentization puts the ball in the OEM's court in terms of making trade-offs between how many features they want to have, how much ROM they want to have, how much RAM they want to have. So in the ideal world, and we aren't there really with the tools for this yet completely, but in this menu, when you're trying to create your configuration file, you have all the trade-offs listed there. When you choose a component, it tells you how much footprint it has, it tells you how much ROM you need for it, tells you all the APIs it gives you, and you can then sort of walk through, and if you're 100 kilobytes above your ROM limit, you can say, okay, I can cut this small thing here and get underneath my limit. So it gives you the flexibility of choosing your point on the curve for your particular device. So to give you a feel for how the configurations work and how low and high sort of the OS goes right now, this is in the ETK we ship a bunch of sample configurations. As I said previously, it's impossible for us to really test the entire 2 to the 200 configurations. So what we've done is we have a little more evolutionary approach here. We've started out with the sort of families of configurations that we test and support. And so we have these 6 different or 5 different configurations that we thought would be useful to address different segments of the market. And we've built configuration files for these, and we ship these as samples. And what we ask OEMs to do in general is not come up with their own entirely unique set of configuration, to start from one of these and only make minor tweaks to them to take advantage of the fact that these are the ones we've tested. So to just quickly run through this, at the low end, our smallest sort of system that you can configure with Windows CE is a pure kernel plus file system, and the footprint for that in terms of, and most of these are ROM footprints. Working sets are not completely included in this because most of our devices are embedded devices running straight out of ROM. So the ROM footprint for that is sort of 250 to 350K. So you'll notice right off the bat that that's probably 5 times bigger than what something like PSOS or VxWorks would be at their low end. And so, in terms of how low we go, that's one obvious point. We don't try and compete really at the, here's the 25K OS that you want to put in your anti-lock braking system. Apart from the fact that maybe you won't want to go there anyway. But you get the point. We aren't necessarily trying to compete right now in the really low end, 25, 30, 50K OS market. What we add next on that is sort of a...
Sorry, how much memory is in a traditional digital cell phone today? So not a fancy browser-based one, but...
A digital cell phone right now is probably about half a meg or so, I think. Now it also depends. In Europe where there's GSM, the GSM stacks are probably about 150, 160K or so of code. Yeah.
I would quote the economist saying the nearest space station has less computing power than some cell phone.
Right. But yeah, I mean, there are very few consumer devices which you'd think of with any kind of UI or something which have less than half a meg or so of things. So when you add the communication stacks, and this is something you could think of in automation controllers, industrial controllers, on factory floors, factory automation scenarios, where you'd be running something like the MinCom configuration. There's no UI, there's not much control, but it's just talking to a host controller which is sort of directing various parts of the factory floor. So that's mostly for headless systems. You can go one cut above that. You can get sort of a support for user input, have a little bit of a keypad on the device, have the concept of input queues for all of your threads. and you can add in core GDI functionality so that now you can have a device with a bitmap display or an LCD display where you can write to the screen, do draw text, things like that, but you don't have a very sophisticated user interface on top of this. So that's what this configuration attacks, and that's about 450 to 750K, again, depending on how you want to configure that. And then you can sort of add in the window manager on that, and then you get most of the hoopla of create window and all of its accoutrements. And then you're talking more in the vicinity of a meg or so of OS code. And finally, you can add onto that things like the shell and a task manager and common controls, common dialogues, and all that kind of stuff. And then you're going more into the 1.5 meg or so range. So that's right now the scalability of CE that sort of addresses it. Goes from about 250K to 1.5 megabytes in terms of the footprint in ROM. Jeez. I'm going to try and breeze through a lot of these now. In terms of communications, we try and support three important kinds of communications. One is between different Windows CE devices. The second one is connecting up sort of to PCs, to host devices, because we do anticipate, and we ship this in lots of companion devices, the palm-sized PC, the handheld PC. So connectivity to your desktop machine is a huge issue for those kinds of devices. And of course, intranets and the internet. In terms of communications hardware that we support, we have PCMCIA slots. We now have USB support for plugging in devices there, built-in modems, Ethernet chips, all that kind of stuff.
Are the built-in modems soft modems, or is it hardware?
There are some soft modems, there's some hard modems. So some of the handheld PC version 1s, in fact, also had soft modems, and some of them in version 2 have soft modems also. Talk a little bit about adaptation. The main parts to think about here are, one, Microsoft does not allow other people to port the operating system to different processor families. So we do all the ports to different processor families. But beyond that, we don't specify any specific bus, memory, interrupt architecture, or any specific sort of chipset for any of the auxiliary devices. And so that porting can be done. And of course, we try and support an installable device driver architecture so that if you have new custom hardware, you can do that.
ETK stands for?
Embedded Toolkit. So this is probably a generic diagram. You can probably explain any Microsoft OS at least with this diagram. But it works fairly well for Windows CE also. So at the bottom end, yes, we do have a HAL, or we call it an OEL to sort of distinguish it from the HAL that NT has. Then we have a device driver layer, the core system services layer, kernel, user, GDI, object stores, file systems, communication stacks. Then we have, these are all the different kinds of APIs that we support on top. The Win32 API, the ActiveX, DAPI, HTML, INET, all these different sort of things. And then you have, of course, the highest level of shell and explorers and remote connectivity, shell applications, all that kind of things. So I think what I'll do is just, instead of going into the specific features, give you a high point of salient characteristics of these different parts of the OS. The OAL, the main intention here is really just to do hardware-specific, put a hardware-specific layer to allow us to move to different hardwares, but to keep it as simple as possible. So unlike NT, which has a fairly high level of abstraction in its HAL, we try and push the abstraction as low as possible. A, because we don't really trust a lot of our OEMs to write too much software. And this sounds funny, but it's true. A lot of the OEMs we work with, people like Casio or other people like that, they don't have a whole lot of software expertise. And if you make them write a complex OAL, they're going to screw it up, and then things don't work too well. Apart from abstracting things like the interrupt controller or the real-time clock and stuff like that, responsibility for the specific power management characteristics kind of resides in the OAL. So the OS has different power-saving modes, but at each transition, it's going to call the OAL to turn specific devices off, because only on your specific hardware do you know which pieces of which chips and which buses or what can be turned off precisely at what point. And of course, the way you make that decision is by deciding how long it takes to turn them back on. So depending on what transition you're making, you're prepared to take more of a hit on the way back up from the transition, and so you turn off the different levels of devices.
Sharad, how much, I assume there's this porting lab situation or something, there's a fair amount of hand-holding or?
Well, certainly till now there's been a fair amount of hand-holding, and in the Handle PC version 1 situation, it was completely sort of done by us. But it's hard for us to scale the hand-holding model. And definitely we can't scale hand-holding for the embedded OS. So what we've done there is, and this is probably a good time to talk about this, in the embedded market, what we have is we have the concept of a system integrator. So we've signed up probably more than a dozen or so companies who essentially make a business out of helping OEMs port Windows CE to their devices, writing device drivers for them, training people in using Windows CE, and all of the associated services for someone trying to get up Windows CE on their hardware. And this is, we're still sort of in the teething stages of that. But that's the only way we see ourselves being able to scale up to supporting hundreds, thousands of OEMs. Because obviously, a team of 20 people here or 50 people cannot do that. We do have a PSS support, which you have to sort of pay through your nose to get. But apart from that, we use system integrators to try and offload a lot of that burden. And for our targeted products, there's some amount of hand-holding that the targeted product groups will do. But even they don't have much expertise really at the driver level. And the Core OS group, again, doesn't have the bandwidth to support all these different targeted product units. And so even there, we have some amount of system integrator work. We have a lot of sample code, which we try to make usable. And there are things we're trying to do to address this, but this is a big problem for us right now.
Do your systems integrators have CE source code?
They have access to parts of the source code as and when they need it.
Okay.
In the device driver model world, just to give you a heads up, instead of whereas at the API level, the overriding concern for us was to keep compatibility with the desktop, because we wanted to leverage all the expertise at the programming level that people had outside. At the device driver level, we explicitly did not try and keep completely compatible with the desktop. There's two reasons for this. One, we couldn't suffer the overhead. If we tried to take the the WDM driver model and put it in for all our device drivers, we'd have too many layers, and at that level, on a small device, you just cannot afford the overhead of that. And secondly, we expected far fewer people writing device drivers, and people who do that are normally a lot more sort of amenable to change and used to writing different driver models. So we have two different kinds of drivers. We have very, very specific native driver models for any inbuilt devices. So devices which have to interface directly to an OS component, like the keyboard driver to our user input system, or the mouse driver, or the touchpad driver. For those, we have very, very sort of customized interfaces so to make those as efficient as possible. And for other ones where we don't necessarily have to be in the middle brokering the driver, we can support the more general stream-based, open, read, write, close model, so that someone who has a unique device can write a driver, write an application, and we can supply the plumbing for them to get at their driver from the application.
Where do things like handwriting recognition plug in?
Handwriting recognition doesn't really plug in at the driver level at all. We have inking support, and it just gets the ink and then just processes point. The handwriting engine itself, the interface is just give it a bunch of points and it returns back a character. So it's a DLL sort of interface at that level. And for some cases, we do have sort of mini driver architectures like the NDIS. We do support that to some extent, but we don't commit to being being exactly the same as the desktop anywhere.
Are the HPCs shipping with USB ports on them today?
The handheld PC version 2 does not have a USB port. The next versions are going to have.
When I saw the USB support, I assume you require a hub since you can't exactly offer the half an amp.
Yes, and we right now don't have both client and host. We only have the host because it's more targeted towards people who want to plug in mice and keyboards using USB to a Windows CE device.
Not for synchronization yet.
We don't use it for synchronization. One last thing at the driver level, because this is fairly important, comes up a lot. Right now, our interrupt model, or our device driver model at the ISR and the communication between the ISR and driver threads is very, very simple. We essentially don't allow anyone to do any work in the ISR. And I don't have to necessarily try and sell you on this. You want to have only one schedulable entity in the system, and having all this time getting stolen away at the ISR level doesn't really do anyone any good. But what that means is we've simplified really our ISRs a lot. We don't nest them. We turn interrupts off for the entire duration of the ISR. We don't even give them access to any stack. We give them access to very few registers. So we cook them. We just, on a lot of these processors, you have multiple banks of registers. So we just switch to a single other bank of registers and dispatch the ISR. By not nesting them, we also don't have to deal with, having to re-enter the bank switching code.
So do people try and cheat on this or not?
Because we cook the ISRs, they can't really cheat too much on it because they'll essentially screw themselves pretty badly. So if you take a long time in your ISR, you've got interrupts off for that much time. Your other ISRs are not doing too well, not too happy. But on the other hand, while this has worked fairly well for us in the devices that we wanted to do, we've managed to do serial ports at 28.8 without any problem. We've managed to do all these keyboards and keypads and stuff. But we have got a lot of flack for this from the embedded market. The people who are doing embedded development are still very much sort of they want to do some amount of work. They're moving gradually to we can do lots of work in the thread model, but they distinctly do not like being told that you can't nest ISRs and you can't do any small computations or anything in the ISR. So this is something that has been a big issue for us.
This reminds me of, this is going to sound horrible, but the original versions of OS2, God knows, 10 years ago or whatever, had an everything is a thread model and nothing done in the interrupt service routine. But you had to have some enormous number of threads cranking before it could say hello world. Things were a little. So I'm interested you can get adequate performance out of this. It's great.
Yeah, and a lot of the key to that is keeping the thread scheduling latency down small enough that you can support this. And for some kinds of devices, it isn't good enough right now. And so part of what we're trying to address, and I'll get to this in the future issues if we ever get there.
How does something as simple as character input work?
Typically, the keyboard driver would just sort of do the scanning of the keypad, and then signal a thread with the scan code that got generated
On a character by character basis?
on a character by character basis. But
So you're doing thread dispatching.
But on some devices, things like debouncing of the keys is actually done at the thread level.
Okay.
Some depends on the hardware, of course. So the kernel, it's portable across processors, so that was probably the single biggest requirement. Right now, the families of processors we support, MIPS, different hundreds, zillions of variants of MIPS, SH3 family, SH4, the x86, Pentium, PowerPC, ARM, Strong ARM. It's a list of processor families that we currently support.
Any DSP families?
No explicit DSP, though the trend for DSP...
Most cell phones use DSPs.
Sure, but the trend for DSP, most of these different families now have variants of their processors where they're integrating the DSP into the processor itself. Or they have auxiliary DSPs.
Like TI has a strong arm and a DSP on a chip, right?
So that's one of the things we're trying to do.
It's still a lot more expensive from a bill of materials point of view
Right,
than DSP
right.
alone.
See, that's the thing, because the cost of DSPs is coming down and the speeds are going up.
Sure, but right now our answer for if you have a main processor and you have a DSP processor where you want to do some stuff, we say run PSOS on the DSP, run Windows CE on the main processor. That's our current approach. We support ROM/RAM execution. We do paging. We already talked about that. We only page in. We don't page out. So we only page in discardable segments. Page out discardable segments. We do use an MMU. This is another big, big sort of issue for part of the answer for how low can you go. We will not go to 16-bit processors. We will not go to 32-bit processors which don't have an MMU. We use the MMU for lots of different things. For sharing, for protection. We use it for fast IPC. When switching between one process and another process, to avoid copies, we sort of mess around with protection bits. So we use it. The use of the MMU is spread widely throughout the system. It would be really hard for us to make a non-MMU version. Now, partly because of us, most of 32-bit processors now coming out do have MMUs. So, in some sense, we have the privilege of being able to affect the market to some extent. So, but that is a line we have drawn right now in the ground, saying we will not put a lot of effort trying to go much lower. We support local heaps, shared memory, all this stuff. We've put a lot of effort into trying to do centralized low memory handling. So instead of having all the applications doing their own low memory management, we try to have a centralized memory management unit which monitors memory being used, and then at various points it invokes this component which can decide what to do with them. So we talked a little bit about how different devices use this. Our process model, it's standard Win32 processors. We do have a limit of 32 processes. If you're interested, this comes from the fact that we use virtual memory, but we run in a single virtual memory address space. There are several reasons for this. One is so that we can enable fast IPC, so that when you switch from one process to a server process, we can allow the server process to look at the client process address space, thereby avoiding the need for marshalling the data and doing any copies on every RPC. So to do that, we have to be able to have a single address space. A single address space also helps a lot in terms of cache usage and not having flushed the entire cache in every context switch. In terms of synchronization primitives, we have a fairly full-featured synchronization set, almost all of the Win32 APIs. And the scheduler itself, right now, is a very standard multitasking preemptive priority-based scheduler. We don't mess around with any priorities. There's no aging of priorities. There's no sort of background manipulation of it. We do support priority inheritance, so we avoid priority inversion problems in the scheduler. We restrict the number of priority levels to 8 right now, and this has to do with the fact that we essentially bound the amount of time that we ever turn preemption off for. So we are, right now, as we ship a real-time OS by our definition, which is that and our definition of our real-timeness is that we have an upper bound on how long it will take for the highest priority thread to be scheduled from when it's woken up. So if you have an ISR, it signals a high priority thread. If it's the highest priority thread, there's an upper bound on how long that will take to run. To be able to do that, of course, your scheduler data structures have to be fairly complex to not have any order n algorithms with preemption turned off. To make that a little simpler, or to allow that, we have in various parts data structures where we have a separate queue for each priority, so that you can do order one insertion and find the next thread to run. To keep the amount of memory usage for all of our system objects down, we kept the number of threads or whatever priority levels down to 8. And by the way, in case this was, a lot of this is private and can't go out on the internet or anything. So I heard Anoop say that this was off
internal
at the end of the last one, but certainly a lot of what I say is not for external consumption. And in terms of where we are right now with our real-time stuff, in terms of average latency, our ISR latency is about 4 microseconds. And this is on a 32 megahertz class processor. And our average thread latency is about 100 microseconds. Our upper bounds are closer to about 20 microseconds for thread latencies and about 500 microseconds for a thread switching latency. So that's the sort of numbers that we stand behind in terms of our real-time response. So that also sort of defines how low the current operating system goes for real-time applications. I'm going to skip most of these. GDI and user, just to talk about the code base. The kernel is a completely new code base. GDI and user are completely new code bases. So all of those three major modules are completely independent code bases from the desktop. And that's mainly because they're so much smaller than the desktop. We'd have to throw 9 out of every 10 lines in NT if we really wanted to use that code base. GDI and user probably have the most complexity in terms of having to be compatible because they bear most of the burden for the app level compatibility.
Can you go back for just a moment? 9
Yes.
out of 10, you said. What are you essentially not doing that NT is doing? Lots more Cartesian product cases, lots more testing at runtime. What are you skipping that they have to do?
Well, number one, we've used algorithms and data structures which are targeted more towards small footprint systems. Probably if you run CE and NT on a 128 megabyte device, CE will run slower than NT. Okay? Because we won't use it. When we do compression, we'll use a 4K buffer, whereas NT will use a 100K buffer. For all kinds of different things, and every step of the way, we've made trade-offs to optimize the algorithms and data structures for small devices and for small footprints. And that sort of defines, in some sense, and was one of our challenges, how high we can go. Because when you do design a data structure, you have to actually design it with some sort of something in mind. You design it for 100 threads or for 50 threads. You don't design it for work really well for 1 and for 1,000. And the second, so that's one. Secondly, we don't carry most of the backward compatibility baggage that the desktop systems have to carry. So in terms of like the Win9X code base, you'd be amazed at how much code there is in there for backward compatibility. Number 3, from NT, we're much less secure than NT. There's a lot of code in NT for NT to be C2 secure. And in every API which takes the LP security attributes, there's a whole bunch of code doing that kind of stuff. Number 4, on things like NT, which are more heavyweight, they also try and do a lot, things like user and GDI are a lot more complex because they have very high cost of switching. So they have a lot of client-side work and server-side work. So for GDI and user, for instance, you have huge client-side libraries, a lot of data structures and things cached on the client side, then a lot of server structures, and a lot of RPC going back and forth across that because they're trying to minimize the cost of RPC. On our system, our approach is basically to keep it as small and simple as possible. We have only server-side things, and we try and make the cost of the RPC as small as possible to keep the code complexity down. So it's really at every stage, and we also don't support a lot of the APIs. And where for APIs we do support, we won't support all the parameters. So depending on how complex things are, we'll knock off semantics if they can't be easily implemented. But it's a constant struggle. I mean, each time we have to add a new feature, we have to go and evaluate how we want to do it. Whether we want to take that code base and try and cut it down, whether we want to take it as is, whether we want to do it from scratch, how much smaller we think we can make it, and it's a constant struggle.
We should try to wrap up in about 5 minutes or so.
Okay. So this is mostly just what features we have.
Talk a little bit about this one.
Just look at Dan, he'll nod.
So the current versions of Windows CE, at least, so let's talk about it at 2 levels. At the code base level, internally, we do not use COM at any level. So there's, we could conceivably, for instance, have said our competitization model every component of the system is a COM object, and everything talks through that, and you have well-defined interfaces and all that kind of stuff. But we just didn't think we had the luxury of introducing that much overhead at that level. We wanted to avoid, as far as possible, any function indirections, any sort of and in fact, for our components at that level, they share global data structures. So the window manager, may have 7 components, but there's a single global concept of the data structure. And so these different components are really in bed with each other in terms of how they know how to access these data structures. So internally, we don't use COM. Now, maybe going forward, some of the parts of the OS might use COM, but right now, at least at the base OS level, yes.
Did you actually evaluate what that overhead would have been?
Yes. And actually, let me correct that. At some levels, like the shell and some of the application level parts, we do use COM. But user and GDI and the kernel and the file systems internally do not use COM.
If you say, we're going to be very rigorous, very religious, we're going to use COM for everything, for all the componentization, what would it have cost you?
We did some amount of evaluation of that, and we felt it would cost us. We didn't do a very rigorous, obviously implement the entire system. We didn't have the time to do that. But we felt it would cost us, probably between 10 and 20% to do
Code
that.
size.
And performance.
Sort of roughly.
But at the application level, we do have COM support. So we have basic COM support in terms of in-proc COM activation, only free-threaded support. So this is a good example of when we had to do COM. Why is our COM much smaller? Well, we didn't do all these complex models. We didn't do a lot of the complex marshalling and that kind of stuff. We just took the smallest amount that we could get away with and did that. We have basic OLE automation. We have basic doc file support. We do support things like ActiveX control, so you can get there. So we have sort of the enabling parts of it. Now going forward, I'll talk about this, but going forward, we are doing more things like DCOM, MSMQ, and stuff like that to allow us to be a more standalone, independent node talking to other nodes in a more standard industrial fashion. And I'll briefly cover that. Java, we have a separate Java subsystem, our own VM, which we implemented, our own class libraries. It's only interpreted this time. We don't have any jitters. We have a VB runtime also that we've done. And we have some amount of shell support, remote connectivity. These aren't that important, really. From what I want to talk a few minutes about is sort of our future focus going forward. Number one, from a sort of product division strategy in CE, we are sort of committed to pursuing this two-pronged approach, the embedded OS and the focused targeted product approach. Going forward, we are planning to move technologies as they get developed in the targeted products into the OS. Now, this is not as simple as it sounds, because when they're done in targeted product groups, they're done in a very focused fashion. Generalize them, compactize them is a fairly big problem. And we are spending a lot of time now in trying to come up with whether we want anything, and if so, what we want to have common in terms of experience across CE devices, whether we want to have the concept of a powered by Windows CE logo on different devices, and if so, what it means. So things like that. In terms of specific OS issues, hard real-time. That's sort of the biggest perception issue that we have in the embedded market for us to be a very competitive OS. And what we think this means, and what we think we need to do to be able to sort of say once and for all and not have all these ifs and buts and people saying, no, you aren't really real time, is to have sub 50 microsecond latencies for thread switching, have nested interrupts, and have more priority levels. So those are sort of the 3 key parts that we need to do to call ourselves or to firmly embed ourselves in the hard real-time space. As I said previously, we are currently bounded, but at higher numbers, and we don't have nested interrupts, and we don't allow more than 8 priority levels. And what we're doing for this, what's most likely is that we will go ahead and do an in-house implementation and probably have a sort of a separate real-time subsystem, but with a high level of semantic interaction between that real-time subsystem and the standard scheduler. So have the same thread structures, allow threads to sort of migrate seamlessly between these different ones. Let me take questions once I'm done. and thereby get the next level. Because we don't believe that trying to implement the same semantics at a high level, we can simplify our data structures enough to get the latency numbers down that much. Because the latency numbers essentially directly map to the complexity of your scheduler data structure. So the second big issue that we have is processor independence. This obviously comes. We get heavily attacked from this, partly because of the threat of Java and Sun and the Java OS. What we're doing for this is we're putting support for MSIL and COM+. I don't know how many of you are familiar with that into our OS. What this does is it's a definition of a bytecode, so it's sort of the equivalent of the bytecode definition of Java, but we think it's better. The bytecode itself is a little more scalable, so you can scale it and make trade-offs in terms of your size performance numbers. So you can make it high level, like the Java bytecode, and have really small size but relatively lousy performance, or you can scale it down so that it's just essentially a machine-independent representation, where you have very fast JIT and very fast performance.
Do you think you'll start creating your apps or your applets?
Yes, yes. We will probably have our Pocket Office and our Office applications coded to this. Because this is a big problem for us in the handheld PC world, where you have 4 different CPUs from various OEMs, and so an ISV writing an application right now has to test it on 4 different CPUs. Not only that, when they write it, so a lot of people wrote applications that don't support all the CPUs, and that sort of doesn't make it a level playing field for the OEMs. It also means that an OEM coming out with a device with a new CPU suddenly cannot run any of the existing applications. So it's a huge problem which we need to address. And what the MSIL runtime also does is it gives us a unified object model and a unified runtime across these different object languages like VC++, VB, and VJ. So it's a very good sounding solution. We have to see how it pans out. And definitely makes us much more competitive with the perceived abilities of the Java OS. I won't really get into what it really does and what it doesn't. The next one, we need to do a lot of work to sort of better integrate into the Windows family to better allow this to be a standalone device and to sort of leverage sales of NT servers and all that kind of good stuff. And so towards that effort, we're doing more work on things like COM+, DCOM, MSMQ support. Working a lot more with things like the Exchange group to do better server syncing up, mail, investigating things like IntelliMirror, zero administration, and all of that stuff. Componentization and scalability. This is sort of at the heart of the OS problem, which is how much can we scale? Number one, we need better tools for our componentization right now. While we have the basic infrastructure in place, it's a bit hard to use, and we aren't really there in terms of the Chinese menu approach. So we need to do a lot of work on that. Secondly, there's a real danger of trying to scale too much. You can't do everything. If you try to be everything, we will basically be good at nothing. And so I've indicated to you various points at which we've sort of drawn the line on. We won't go lower than this. A good sort of high line is just if there's any place where you could sell NT or anything like embedded NT, we won't go there. Because it doesn't make sense for us to go there. NT makes a lot more money as a shareholder. I'm much better off having NT being sold to them than Windows CE. And so that's a big issue for us, however, because all of these handheld PCs, the next version of the handheld PC is a bigger thing. It's more like a sub-laptop. And the kinds of features they want are more, getting higher and higher end. And so they want more and more of NT-like features. And so as sort of Moore's Law kicks in for these devices, the devices are going higher end, and they want the OS to scale with it. However, from an OS perspective, we try and not write Moore's Law up in terms of, we'll double our requirements each year, but we try to write it down by saying we'll keep our requirements the same and effectively go lower and lower each year. So because of this conflicting sort of approach to Moore's Law, the scaling that we have to do gets vaster and bigger every year as more devices and more products come out. And so that's a big issue for us going forward. and sort of, in the same train, keeping things small and fast. OSs and software, the more people you put in it, the more time you have, the more features you put in, keeps getting, bigger and bigger. And, that's the biggest, concern people have with Microsoft shipping an embedded operating system. It's, well, next version will you be twice as slow and twice as big. And that's a real issue for us to keep, and it ties back into our computerization strategy and how we can, what things we can do to try and keep things small and be able to keep a small OS.
Sharad, given the fact that OEMs can select which pieces they're going to implement, what are you going to do for some standard API set for your bytecode for MSIO?
Well, the bytecode doesn't really define an API set.
Well, I know, but if you write an app, you're going to call APIs.
So let me address that.
We should try to finish up here.
I'll catch you later.
Okay. We're doing some work to do a better reference platform to be able to map the sample code better. Just sort of, I've talked about most of these people, but our big competitors really are Sun with Java, because they have a lot of mind share, and they have a lot of this promise of portability, and sort of touching on what Dennis mentioned, they've gone into this sort of, here's a Java for phones, and here's a Java for this category of devices, and so they have these category level APIs that they're trying to promote. So for us, we're trying to do MSIL to attack that, and we do have some amount of work going on to try and attack the device categories. And then at the embedded market, people like ISI and Wind River, they're a lot, they're established, they have smaller OSs. Probably the biggest advantage they have over us right now is the fact that they have a strong field engineer sales force. The way sales are made in the embedded market right now, people go out to customers and demonstrate it and show them everything, and we don't have any such thing. And that's a huge problem for us right now. We are trying to ramp up somewhat of a sales force, but it's an issue for us.
So the revenue model is the customization they do in things? Or?
The revenue model is that ISI, the different embedded OSs basically don't make money off royalties. They make money off their tools. They sell their tools for a lot more money, and they make money off their consulting services.
Right.
And we are trying to make money off the royalty, but not off the tools. Give the tools away for free and not do consulting. Now, part of this plays together. Now we're actually talking to these companies and trying to make them support Windows CE and get consulting revenue from us. And say, since you aren't getting that much money from the royalty anyway, get your money from doing Windows CE stuff. But it's a complex equation that we have to sort of walk this fine line on. Finally, just a summary sort of slide. Windows CE is definitely a platform. So we don't try and attack markets. We don't try and attack device categories where there isn't need for a platform. So if you have a completely closed system where you have no interaction with other things, it's highly likely you'll probably be better off going off with PSOS or VxWorks. Our strengths as a company are in creating platforms, evangelizing platforms, and so that's what we're sort of doing. I talked about Moore's Law. I talked about having to add features, and this is a big issue. And as a marketing strategy, we're definitely trying to go for volume in terms of getting revenue. So hopefully that covered most of your hot spots.
Great. Thank you very much. So I think what we should do at this point is basically push the agenda back.
So the revenue model is the